let us start this one now. Okay, after that one, we learned this. I hope that you agree that if Q is a refinement of P, we have this inequality. Yes, because L, F, and P will be definitely less than LFQ. LFQ is always less than UFQ because they have the same partitions, and lower sum is always less than or equal to the upper sum of the corresponding partition, and this one is the theorem. So you see, this part is the theorem. This part is also the theorem we just proved, but this one is based on the definition of lower sum and upper sum. Yes, that's cool. Okay, so now the interesting one is this lower and upper integrals. So let me just define it here for you instead of going through the notes. So 11 and 19. 11, 19. Okay. What is the meaning of an lower and upper integrals? So again, I have a function from AB to R, and it is bounded. Okay. So let me ask you one question. Let me open up a set, and then I calculate all. If I want to define which one, I have to find first the lower one. So okay. So I will write this L, F, P, and P. Okay, so from now on, when I write this P, I'm a little bit lazy. It's when I write P here, it means P is a partition of the interval that I am working on. Okay, so for simplicity of writing, when I say this vertical line P, P means this sentence. Okay, so can you see, so forget about this slide. If I ask you what is this set, do you agree that this is a subset of R? So do you agree this is a subset of R? Why? Because every lower sum is a real number. We calculated one of them for you, for example. It's a bunch of numbers. Function is fixed from the beginning, but how many partitions I have for my interval? Infinitely many. Imagine that for every partition possible, you calculate the lower sum. You get a set of infinitely many real numbers. Is that right? But that set is a subset of R, and clearly it is not empty. Why this is not empty? Because at least I have one partition, and the partition is X naught and X, A and B itself. Okay? So it is not empty. But one more thing. Do you think that this set is bounded above? Is this set bounded above? Yes, why?
Because
we just had a formula. Do you remember? Little m b minus a. Yes, you are saying what you are saying is also true. Yes. But this one will work for both of them. We learned that every lower sum is greater than or equal to this threshold. What was m? F of x was between m and m. If this happens, and this can happen because this is bounded, and this is less than this one, less than this one, and then do you remember, less than this one. So this means that these numbers cannot go beyond this threshold. So they are bounded above. So bounded above. Yes. Or, as you said, it is always less than this number. Okay, so can I talk about the supremum of this set? Can I talk about the supremum of this set? Yes, because it is bounded above and it is not empty. So it has a supremum. So this supremum always exists. This number is called the lower integral. So we call it lower integral of my function from a to b For denoting the lower, we put a line below it. That's called the lower. So there is no confusion. This number always exists and it is a real number if you respect that your function is bounded. And if I go here, instead of putting the lower sums in a set, this time let me put the upper sums in a set and run this partition on all possible partitions again. Again, this is a subset of R, this is non-empty, but do you agree this is bounded below this time? Yes, because UFB, they are bounded below by this number. So it means it has an infimum. The infimum of this one is called the upper integral of F. Yes. So these two numbers, you can always find them in the real numbers if you just respect that your function is bound. Okay? But there is no guarantee that these numbers are the same. Okay? So, any questions regarding this? So, do you understand what we are doing? So, if geometrically, what is the meaning of lower sums? The lower sums is the sum of internal rectangles. Okay? What we are doing, we are finding somehow the highest bound, the maximum of the possible sum of the areas of the internal rectangles. Okay? They are approaching to the area from below. And this one was, what was that, do you remember? This one is, every one of them is a sum of exterior rectangles. But we are finding the infimum of them. Okay, so the infimum of them is guaranteed to exist, the supremum of them guaranteed to exist. But if my function is a well-behaved function, we expect that these two numbers at some point meet to be the same. If that is the case, which is not always the case, if these two numbers turn out to be the same, then we can call it integrable. And that number is the area below the curve. Okay, but now one question. These numbers always exist. What is your intuition based on this geometric picture? That is the content of the next theorem. Is there any order relation between them? Because you know that LFP is always less than UFP. But in this one, we are taking supremum. In this one, we are taking infimum. Okay? But intuitively, do you think that one of them is always greater than or equal to the other one or not? You see, it is not that obvious. You have to prove it. Because even though every element in this set is smaller than some element in this set, but here we are taking sup, here we are taking inf. So it is not very clear that which one finally will dominate. Okay, but what is your intuition about X in this geometrical way? Yes?
I might be wrong, but the lower one is always smaller than the...
Yes, that intuition is correct. And that is the topic of the next one. So 1120. So it means that integral, the lower integral, is less than or equal to the upper integral. Okay, so to prove this, what we need to do is to do this. If I write L, F and P, and if I write U and F and the same P, you always agree with this one. This is always true. So let me write a sketch of the proof. Okay? But one thing matters. What I'm saying is that if you just choose two partitions, can I always write this as well? So this one is trivial. We had it before. If the functions, the function is always the same. If the partitions are the same, of course the lower sum for that partition is less than or equal to the upper sum for the same partition. But if I choose two different partitions, one P, one Q, even if I don't know one of them is a refinement of the other one, no. There are just completely random choices of partitions. Is it still true that the lower sum of any one of them is still less than the upper sum, even though the partitions are not the same? I want you to understand this is more or less trivial, but this is not trivial. We have to justify that. And when you justify that, I will leave it an exercise. You can read it in the notes to prove this one as well. But why do you think this is correct? Yes?
Because the upper sum is, if we look at it as an area, it's always greater or equal to the area.
No, that's intuitively,
Yeah.
but rigorously. Yeah, you are right, but rigorously. So L, F, and P, okay, do you agree this is less than or equal to L, F, and P union Q? Do you agree with this one? Because we proved this is a refinement. Yes? If you give me two partitions, P union Q is the common refinement. So this P union Q is a refinement of P. So this is correct, because that was the topic of the theory. But this one is correct or not? Because I haven't changed the partition. I kept the partition the same, so it is more or less like this. The partitions are the same. Yes? But again, I can write this one less than or equal to what? Is that right? Because now this is a refinement of Q as well. And in the refinement, the upper sum goes down. So it is a combination of some small theorems. Okay? So this is the proof of this one. And then try to go home and then prove this one using this idea. Okay, so now let us go to the definition. This is an important definition. For example, I might ask you to define Riemann integrability in the exam. This means that you are supposed to write this. Okay? So Riemann integrability and Riemann integral. So let us read it. Let f be a bounded real-valued function on a closed interval from a to b. We say that f is Riemann integrable on a and b if the lower integral is equal to the upper integral. That's the integrability definition. And this is the symbol we use, the curly R for Riemann. We say f belongs to this. If f is Riemann integrable, then this common value is called the Riemann integral of f on the closed interval a and b, and we just simply denote it by the integral from a to b f. And hopefully you see the difference. In calculus, you write integral from a to b f of x dx. But I hope that you understand there is no need to put an x there. Okay? Integral is a number that I associate to a function and an interval. So that is enough to have those information in its notation. A and b and the name of the function f itself. So is that clear? So this is the meaning of integrability. So for example, this could be the case that I can ask you in the knowledge base. What is the meaning of Riemann integrability, and define it, or something like that. Okay, so,
Well,
yes,
can I ask you a question about the previous slide?
yes.
What do you mean by
Riemann integral.
or like the R, then square brackets AB?
Yeah, I will explain it here on the board. Okay, so these are good symbols to learn. So what I'm saying is that this is always a number, this is always a number, and this theorem tells me that there is no guarantee they are equal. It is guaranteed the lower one is smaller than the upper one, but there is no guarantee that they are the same. In some cases, they happen to be equal. In that case, if they are equal, we say that f is Riemann integrable. Instead of writing it in English, Riemann integrable, we say f belongs to this. So this, when you see this, it means f belongs to the set of all Riemann integrable functions on this closed interval from a and b. Okay? It means that if you see this symbol, it is equivalent to saying that lower integral is equal to the upper integral. That's the meaning. Did I answer your question?
Yes.
Okay. So, for example, that's good to you ask. So there is also a symbol for continuous functions on the closed interval. So usually we write it like this: curly C, A and B. So if you see this, what does it mean? F belongs to this. It means F is continuous on A and B. These are the symbols. Yeah. Okay. So now, this example and the next example are central examples because they will make you understand. They are extremely simple, but you understand the meaning of this integrability. So let us understand that. This is an extremely simple calculus one, but I don't want you to do using calculus. Be careful. So let me just explain it here. Consider the constant function f of x equals to c, where c is a real number. Show that f is Riemann integrable on any closed interval from a to b, and the integral of f from a to b is c times b minus a. Okay? Okay, so I just want you to understand that what we are doing is very trivial in calculus, yes? If I have a constant function, so if I ask you, do you remember in calculus, or even in high school, if I give you this, and I ask you to calculate this integral, so what do? You find a primitive function for this constant. What is a primitive function? A function whose derivative is c. What is that function? Cx, yes? In the high school way. And then you go from A to B. You replace this with B, you replace it with A, and you subtract them, so it becomes B minus A. But if you write this in the exam, you will get 0. Okay? So, but this is not completely irrelevant because that is the genius of Newton, actually, who realized there is a relation between integral and derivative. Okay? That is very subtle. The way I presented the integral, you don't even need the notion of derivative. I even didn't start teaching you derivative first. I just started teaching you integral without the idea of derivative in place. So this means that these ideas are not related to the derivative, but extremely cumbersome. You will see that. That's what I want you to see once. This way of doing it from definitions is very cumbersome. So that was the genius of Newton and Leibniz, who discovered that there is a connection between the integral idea and the notion of derivative and how they can help each other to actually calculate the integrals. Okay, so for the time being, what I am doing is actually extremely elementary in calculus, but we want to do it in the hard way. Okay, so you help me. So do you understand what the question is now? So 1122, I have given you a function which is a constant function. If a function is constant, definitely is bounded, so it fits to our theory of integration because we are only working with bounded functions. So that's okay. But now I want to show that this function is integrable. So what should I do? Tell me. According to the definition, I have to calculate the lower integral, I have to calculate the upper integral, and convince you that these two numbers are the same. If I can do that, the common value is the integral. Is that clear? So I want you to help me. So if first I will write the definition, the integral from a to b, the lower one. What was the definition? The definition is the supremum of all lower sums. I am using still this convention. That is this. But let me calculate one of them to see which one is that. So I would say let P be this x0, x1 up to xn. Be a partition of A and B. Okay. So L, F, and P, I write the definition, is sigma, you remember, little mk, delta xk, k goes from 1 to n. But I'm waiting for you. I have to fill up this. This is one of the terms here. But what can I put for m sub k? M sub k is the infimum of the values of my function, this function. If you draw the graph, is a little bit helpful, but your argument should be independent of the graph. The graph is a horizontal line. For example, let us say that C is positive here. So this is my line, horizontal line. Okay? So I am looking to my function here, and I have chopped it into smaller pieces. So can you tell me what is m sub k here? M sub k is the infimum of the values, or the minimum of my values in the kth interval. So what is the minimum of my function? Yes?
It's C.
It's C itself, because it's horizontal. So all mk's are C. So instead of mk, I put just C. But C is a constant. It doesn't depend to the counter, so I can move it out. But this is a formula. What is the formula for? This is the sum of all the lengths of subintervals. If I add them up, it becomes the total length. The total length is equal to b minus a. Okay? So what does it mean? It means that integral of a, b, f is the supremum of. All of these numbers are not different numbers. So all of them are the same. Even though I have infinitely many partitions, but this infinitely many partition, all of them give rise to the same number. So this set has only one element in it. And if I want to find the supremum, it becomes the same number. Do you agree? Okay, so I don't want to write it down because it's extremely simple. Do you agree that the other one is infimum of the upper sums? So the upper sums, the difference will be this little m becomes capital M. But what is capital M here? Everyone, what is capital M?
It's the max.
Again, C. So it doesn't change anything. So it means that all of them are also having this number inside. So if you calculate this integral from a to b up, this becomes infimum of again the same number. Okay, there is only one single number here. Infimum is the same. So it means that the upper integral and the lower integrals are both equal to the same number. So this means that these two are the same. So this means that integral from the lower integral is equal to the upper integral is equal to c times b minus a. So this means that, first of all, because they are equal, that is integrable, and the common value is the integral. So everything is finished. It's a very, very simple exercise, but it is very good to understand the concept. The next one is also very important. This is also an important concept. This is a famous Dirichlet function. Do you remember? The output of the Dirichlet function is either 1 if it is rational or 0 if it is irrational. What we learned about this, I just want to refresh your memory. So what we learned about the Dirichlet function at some point? Yes?
Continuous.
It is not continuous at any point. This is one of the functions that doesn't have even one single point of continuity. It jumps up and down so much. But be careful, if I give you this in the exam and you say that it jumps up, up and down, this is intuitively clear, but you have to write it correct. Okay, this one was not continuous, okay, but I want to show that this is also not integrable. This is a very simple exercise, but I want you to help me to do it together, okay? there is no way I can draw the picture for it, but you know that it is either 1 or 0, depending on if the input is rational or irrational. Imagine it, but try to see if this is integrable or not. And I want your help. Okay, the first thing I want to do, this is example 1123. So what I will do is this one. Integral from a to b, the lower integral. So, yeah, be patient. In the exam, you just write the definition. So supremum of L, F, P, and P. But in the exam, you write P is a partition on A and B. Okay, so let us take the P, this one. Let P be this, any typical one. And I want you to help me to calculate the lower sum for this one particular P. But that is an arbitrary one. If I can manage to calculate this for an arbitrary one, it means that I know all of them. So how do I write that? There is only one formula. This is sigma little m sub k delta xk. K goes from 1 to n. So what is mk? Let me write it a little bit more carefully here. Mk is the infimum of what? Of f of x's such that x belongs to the kth interval. Okay, I want to wait for you. First of all, can you tell me within this set how many numbers you see? Read it. The values of f of x where x belongs to this particular subinterval. I don't know where is this number, I don't know where is that number, but I know this is an extended interval. X sweeps all of it and that calculates the values of f of x, and we put it in this set. So how many numbers are there in this set? 2. What are they? 0 and 1. Yes, because if you reach to a rational number and you send a rational number here, it gives you 1. And if you reach to an irrational number and you send it here, it gives you 0. And your number is either rational or irrational. So there are only 2 numbers here. Yes, so this is just infimum of what? 0 and 1. And the infimum of 0 and 1 is 0. And I put it back here. So this becomes sigma, k goes from 1 to n, 0 delta xk, which becomes 0. And now, if I write u, so, okay, now let us calculate this one. So what is your opinion about the upper integral now? So it becomes supremum. How many elements are now in this set? All of them is 0. So this set has only one element in it, and that is 0. And if I ask you what is supremum of 0, it is 0. Is that right? So let us repeat this quickly for the upper sum. So if I calculate this one, you will write it with the capital Mk. K goes from 1 to n, delta xk. And if I ask you what is capital Mk, you will say this is the same set, but it's supremum. Okay, but this set is the same set. So if it was 0 and 1, it is still 0 and 1. So it becomes supremum of 0 and 1. But this time supremum is 1. Okay, and then I go back here and I want to write the definition of the upper sum, upper integral. So this becomes infimum of u, f, and p, such that p is a partition. But this one has only one element in it, because no matter which partition I choose, UFP is always 1. No, sorry, I was in a hurry. So I put it here. What is the answer? Because MK is calculated, I have to put it here. I was in a hurry. So what's the answer now? It's the sum of all the lengths, it's D minus A. Okay, so now this becomes infimum. All these are the same number. And if I ask you, there is only one element here, so its infimum is B minus A. Okay, and now you see that the lower integral is 0, but the upper integral is b minus a, and b minus a, oh, I was, sorry, you know why? I am taking partition from a to b in my solution. The partition is from, okay, at the end I can put the numbers. 1 minus 0 is 1. Okay, and this one is 0, this one is 1, and they are not equal. So this means that the regular function is not integrable. Is that right? This is a very simple exercise. I want you to know. Any questions? Okay, so let me also write this one, and then we are done. Might be we will not be able to prove it completely, but this is a fundamental theorem, Riemann integrability criterion. So I just want to motivate you why we need a theorem. You see that these are extremely simple functions. I hope that you can see that if the functions are complicated, calculating u, f, and p for a generic partition can be cumbersome or even impossible. Because these functions were so simple in structure, I was able to calculate these things exactly. So the people who actually developed the notion of integral, they also knew that this is not always a good practical way of calculating integrals, because if the function is a little bit complicated, we don't know if the function is integrable or not, using the definition, going back to scratch, from scratch and see if it's integrable or not. So we wanted to develop a theorem that guarantees integrability, exactly like compactness. Compactness was hard. We tried to find another theorem which was intuitively easier to understand the notion of compactness. So now here we want to have another criterion in our hand to have a better definition for integrability. Okay? So this, let me explain it here. Might be we can do the proof next time, because that's a very fundamental theory. Okay, so now let me just explain it for you. Only explanation. So 1124. The proof is of course in the notes, and the proof is very important if I want you to understand this kind of proofs. Okay, so I give you a function which is bounded on the closed interval. Yes. And I want to know if f is integrable or not. So f is integrable if what happens? If the upper integral is equal to the lower integral. But it is usually hard to check. But this one is easier and more practical to check. F is integrable if and only if every epsilon that I give you, you can give me a partition such that the difference between the upper sum and the lower sum is less than epsilon. So in other words, it is not guaranteed that every partition will satisfy your epsilon. But it matters like this. If I give you any epsilon, even if I make this epsilon extremely small, still you can come up with a partition that makes this difference less than epsilon. For example, you see why this Dirichlet function was not integrable? Because the difference between L and F, L and U is 1, L is 0. The difference between them is 1. So I cannot make it arbitrarily small. 1 is not a big number, but that is the dead end. I cannot make it smaller than 1 because the difference is always 1. But if I can make this difference smaller than any pre-assigned positive number, then this is integrable. As we will see next time, this one is easier to check for integrability rather than this one, because there will be another theorem coming after that, which is called Archimedes and Riemann theorem, and it is also easier. You don't need even to work with any partition. You can start working only with regular partitions. Yes?
Why don't we just say that the difference between them are 0?
That is the ideal scenario.
Okay.
Yes. So if, of course, if the difference between them is 0, it is already integrable because it is smaller than any possible number. So be careful. This is not a fixed number because f is fixed. When I ask you to calculate this one, when I give you f, you cannot still start calculating this because to calculate this, I have to give you f and p, and p is not fixed. F is one fixed function, but P can be infinitely many, there are infinitely many partitions. Yes? So we cannot say that even if the difference between two of them is a constant number, the difference was 1, in this way I prove that the difference between any two of them is 1. Okay, but if I can manage to show that the difference between two of them is 1, there is no guarantee the difference between the other two ones are still 1. Because I am changing P. Is that understandable? Okay. Any questions? Okay, have a nice weekend. Yes, thank you.
Thank you.
Thank you.